Laplace transform. The objective of these topics are as follows. At the end of the topic, students are able to define the Laplace transform. Second one, obtain the Laplace transform of given functions by using definition. Introductions. It is an integral transform which transforms functions of one variable to function of another variable. Nowadays, the Laplace transform is very important tool to scientists and engineers in finding the solution of partial and ordinary differential equations with suitable given initial and boundary conditions. When Laplace transform is applied to such equations, they get reduced to algebraic equations, which are easier to solve as compared to other methods. We get directly particular solution to these differential equations by Laplace transform. We can also use Laplace transform to evaluate some improper definite integrals. Now, definition of Laplace transform. Let f of t be a function of t for all t greater than or equal to 0. The definite integral 0 to infinity e to the power minus st f of t dt, if it exists, then it is called Laplace transform of function f of t and denoted by symbol L of f of t. That is, L of f of t is equal to a definite integration limits from 0 to infinity e to the power minus st f of t dt, denoted by equation 1. Here s is a parameter which may be a real or complex number. Note that the value of right hand side integration is a function of parameter s, so Laplace transform can also denoted by symbol f bar of s or simply f of s. Therefore, with this notation, L of f of t is equal to f of s. Now, using the definition, we can see some examples. By using definition, we can find Laplace transform of some simple functions. Example number 1. Find the Laplace transform of function f of t defined as f of t is equal to sin t if 0 less than t less than pi, f of t equal to 0 if t greater than pi. Now, by solution, by definition of Laplace transform, Laplace transform of f of t is equal to a definite integration limit from 0 to infinity e raised to minus st f of t dt. Here f of t is not a continuous function, it is a discontinuous function, so that we have to split the range of t from 0 to infinity into a sum of two integrals. First integral when t 0 to pi e to the power minus st f of t dt, and plus second integration t from pi to infinity e raised to minus st f of t dt. From the given hypothesis, when t between 0 to pi, f of t is given as sin t, and when t between pi to infinity, f of t is given 0. So this is equal to integration 0 to pi e raised to minus st sin t dt. So after integrating e raised to minus st sin t with respect to t using standard formula of integration, so we get e raised to minus st upon minus s square plus 1 square in bracket minus s into sin t minus 1 into cos t when t running from 0 to pi. After putting the limits, first upper limit e raised to minus pi upon s square plus 1 in bracket minus s into sin pi minus cos pi, then minus in bracket. Now put the limit t equal to 0, lower limit e raised to 0 upon s square plus 1 in bracket minus s sin 0 minus 1 into cos 0. but we know that sine 0 equal to 0, cos 0 equal to 1, sin pi 0, cos pi minus 1, and e to the power 0 equal to 1. Therefore, Laplace transform of f of t is equal to now 1 plus e raised to minus pi upon s square plus 1. Now example 2. Find the Laplace transform of f of t defined as f of t equal to 1 if 0 less than t less than 1, f of t equal to t if t between 1 and 2, and f of t equal to 0 if t greater than 2. Again, by definition of Laplace transform, Laplace of f of t is equal to integration 0 to infinity e to the power minus s t f of t dt. Here again the function f of t is a discontinuous function. It is split into 3 parts. Therefore, the whole range of t from 0 to infinity can be split into sum of 3 integrals. One is 0 to 1 e raised to minus st f of t dt plus integration 1 to 2 e raised to minus st f of t dt plus integration 2 to infinity e raised to minus st f of t dt. Put the value of f of t which is equal to small f of t given in hypothesis. When t between 0 to 1, f of t is 1. When t between 1 to 2, f of t is t. And when t greater than 2, f of t is 0. So therefore, we get 0 to 1, integration 0 to 1 e raised to minus st dt and plus integration 1 to 2 e raised to minus st into t dt plus integration 2 to infinity e raised to minus st to 0 into dt. So the integration of e raised to minus st is e raised to minus st upon minus s when t from 0 to 1 plus. Now the second integration can be evaluated using integration by parts. We get t into e raised to minus st upon minus s minus 1 into e raised to minus st upon s square when t running from 1 to 2 plus the third integration vanishes. So after putting the limits in first bracket 0 to 1, first t equal to 1 upper limit, we get minus e raised to minus s upon s, then minus when t equal to 0 lower limit, then we get minus 1 upon s, minus minus becomes plus e raised to 0 upon s, then plus. Similarly in the second bracket, when we put the limits of t from 1 to 2, we get minus 2 e raised to minus 2s upon s minus e raised to minus 2s upon s square, then minus in bracket when we put t equal to 1 lower limit, we get minus e raised to minus s upon s minus e raised to minus s upon s square. So after simplification, we get Laplace transform of given function f of t is equal to 1 minus 2 e to the power minus 2s upon s and plus e to the power minus s minus e raised to minus 2s upon s square. Example 3. Find the Laplace transform of a function f of t defined as f of t equal to 4 if 0 less than t is less than 1 and f of t equal to 3 if t greater than 1. Again, by definition of Laplace transform, Laplace of f of t equal to 0 to infinity e raised to minus st f of t dt. Here function f of t is again discontinuous function and its value given as 4 and 3 according to the interval of t 0 to 1 and t greater than 1 respectively, so that the whole range 0 to infinity can be split into sum of two parts. The first integral having limit 0 to 1 e raised to minus st f of t dt and second integration having limit 1 to infinity e raised to minus st f of t dt. Now put the values of f of t which is given. For range 0 to 1, f of t is 4. For range 0 to 1 to infinity, f of t is 3. So after integrating first integral, 4 constant outside, e raised to minus st upon minus s when t from 0 to 1 plus in the second integration 3 constant outside, you can write the integration of e raised to minus st is e raised to minus st upon minus s when t running from 1 to infinity. So in first bracket, when we put the limits of t from 0 to 1, we get 4 in bracket minus e raised to minus s upon s plus e raised to 0 upon s. Then plus 3 as it is in second bracket, when we put the limits of t from t equal to 1 to infinity, we get in bracket minus e raised to minus infinity upon s plus e to the power minus s upon s. But we know that e to the power minus infinity equal to 0. So by using this value, after simplification, we get Laplace transform of given function f of t is equal to minus e to the power minus s upon s plus 4 upon s. So knowing this procedure, you can solve the following few examples as an assignment. Question: find the Laplace transform of following example. So there are 4 examples given here. You have to find the Laplace transform of these 4 examples using definition of Laplace transform.